Well, we're just about there, folks. Welcome back, everyone. It might be a small class today, but we'll definitely get through it. And I'm blaming Super Bowl and Valentine's Day for this. So it's always going to be weird days like this where classes might be light. And if that happens, keep in mind you can always find the lectures here for each one of our class meetings. But before we get started, let's take a look at the announcements. Our exams are all been graded over the weekend. And for each one of our exams, once I've graded the whole set, I'm going to post the solutions up here on the Moodle website. That way you can double check your work. You can all use this as a resource to study for the final exam. I'll also post summary statistics, pretty basic stuff. So I usually post the average. I usually don't put the standard deviation or the median or anything wild like that. But it's also kind of interesting to see the top 3 scores. So I usually post those as well on each exam. So any questions, folks, about the exam at the moment? Okay, I did want to make one note about the exam that I think is actually a little bit confusing. If you take a look at, let's take a look at maybe this document. You really have 2 scores. The first one is just your percentage out of 100 points possible. Your second score, called your course score, this one is also posted to Moodle. And the way it's calculated is, let's go over here to the syllabus. Your course score is weighted 30% of all the homework that was due. And your exam one is weighted as, well, it's quite a lot, 70% at the moment. Once we go to exam 2, exam 1, exam 2 will each be worth 35% and so on until we actually have the final exam on the table. So pretty much I'm going to report a course score just based off of what we have, giving us our best idea of where you're at in the class right now. And after every time something's graded, your course score will update. So it's always a good idea to come back here, double check it, and make sure nothing's missing. That can definitely happen when so much data is moving to and fro. I would definitely check this out in every one of your classes. Make sure you always get your scores put in correctly. Well, that was the one comment I definitely want to make about the exam. Other questions or comments so far, folks? Give me one moment. Other questions so far, folks, about the exam one at the moment? Okay, well, after getting through the exam, we're pretty much going to repeat the same pattern you see on the Moodle website, almost verbatim. So right now, here's the week we're currently in. As we scroll through, we've got midterm week we're going through. There's nothing special happening on midterm week. I just report your course score as it is on that week. And our second exam is going to appear right around here. So as we get closer and closer to this date, right before spring break, you'll start seeing the definite coverage for the exam as well as things like the review materials and so on. And so we're just repeating everything you see on the Moodle website. But other questions or comments, folks, before we jump back to section 1.9? Okay, well, we almost finished that section. We're on the very last problem. There's an application after that, which is optional. I'll leave it up to the class to decide if we want to cover that one or skip it. It'll be our decision. So in section 1.9, well, we didn't quite start off this way. Let's maybe go to the very top since it's been quite a while. So it started off with definition of linearity. We're really just doing a continuation of studying the linear transformations. And transformation is linear so long as it takes vector addition right here and preserves the operation right here. Also, this has to work for all vectors U and V, as well as all scalars. The scalar multiplication here should also be operation preserving. So C factors out, and we have a scalar multiplication over here in the codomain space. So if those 2 simple properties hold, it causes massive ramifications in mathematics, and this is why we like linear transformations. It's simple properties, which turn out to be really powerful properties all at the same time. We looked even further about these linear transformations. The ones we're also particularly interested in, after we scroll through this, are the ones that are one-to-one or injective. One-to-one could be thought of as every time you map something to, say, a vector B, you have at most one X that can map that way. There's lots of ways to define this. This is just the author's preferred method. But for thinking about one-to-one, let's write down another equation. Sometimes one-to-one is defined in this way. If T of X equals T of Y implies X equals Y, then T is 1, 2, 1. In other words, if T of X maps to the same place that T of Y does, well, X and Y had to have been the same exact vector. So that's one way to think of one-to-one. Our author's definition is more a linear algebra approach because he wants us to connect these dots when we think about one-to-one. That there's a unique solution to the homogeneous equation, which means no trivial solutions to this thing. That means there's no free variable, the columns are linearly independent, and that's how we typically like to think about one-to-one. Linear independence is just the foregone conclusion. Likewise, if we're thinking about an onto mapping, I think I scrolled too far, there we go. An onto mapping is just saying, well, we have consistent for all possible vectors B in the codomain space. This would mean Rm is the range. Every single vector in there can be accessed by the right vector in the domain space. But all the logic just boils down to this. Your mapping is onto just means there's a pivot in every row for the standard matrix A. So we took all that information, collected them down into some theorems. If they are, there's the theorems. But when you use those theorems, there's another way to think about this. If the columns of A span Rm, that's just another way to think about. Let me make sure this is going to work. There we go. Another way to think about this one is that there is a pivot in every row. And this is where it gets dangerous to conflate rows and columns now, because it could be saying something entirely different if you mention column instead of a row here. So let's put that one in green just to emphasize it. Next one, if we're talking about T being a one-to-one mapping, the columns of the standard matrix have to be linearly independent, but we can boil that down to just saying there's a pivot in every column. So really powerful theorems, and all the linear algebra just boils down to where's the pivots. In other words, row reduction is going to identify everything for us. Well, this is just meant to be a really fast concept kind of question at the end of the notes. I deleted this one because I looked at it again and I realized I was asking the same exact question. I'm not sure why I wrote that one. I left it here just to explain why something got deleted. Let's start off right here on example 5, part A. It says T is mapping R4 into R3 in a linear way. So we have a linear mapping for sure. We want to know if T is one-to-one. And sometimes it's kind of fun to guess with this. The domain space is 4-dimensional. We kind of live in a 4-dimensional space, space-time. Mapping into something with 1 dimension less, that means a whole bunch of vectors are being essentially glommed together to get into that 3-dimensional space. There should be no way for that to be one-to-one, but we need to explain that in a linear algebra way, not with intuition. But if you can think of it in an intuitive way, that's a good start as well. Here's how we'd have to attack it through linear algebra. If they tell us the mapping is linear, the very first thing you want to do is write out this. Since T is linear, T of X equals AX for all X in, we have to mention the domain space, so this would be R4. Now that we have the standard matrix A, we can attack through these theorems, determine where the pivots could potentially be. Let me just fix the penmanship first, that should help. So this gets us started, but if we're going to decide what the pivots are, we should know the size of that matrix A. Anyone happen to recall what its size should be? There's a definite trick to this if we're not sure. So what you want to do is kind of just follow your nose right here. We said all x in R4, so work backwards. The size of that vector x has to be 4 by 1. Then if we work backwards to the matrix A, let's put a question mark here just temporarily. It'll have to be some size by, well, by 4 for sure, because the multiplication is not even compatible unless those two dimensions match, the number of columns versus the number of rows. But we could also find the size right here. Anyone happen to know how many rows A must have? Exactly. Once we get this one nailed down to over here, then we just grab the leftover. That's the number of rows for A. So A is of size 3 by 4. And this is how people typically memorize it. I mean, you don't want to necessarily reverse engineer it on exam, right? Would take extra time and it's stressful to do that. The trick is it went from R4 to R3. It's 3 by 4. So you just swap those and you're always on the right track. Oh, didn't need to scribble on it. Let me pull that off. So that's the major punchline. If you can say what the size of the standard matrix A is, you're in really good shape now. Let's write out a generic matrix A of that size. It needs to have 3 rows. There it is, 4 columns. And we don't know at all what the pivots are on this. There could be no pivots. It'd be a 0 matrix in that case. All entries are 0. Maybe there's exactly 1 pivot. But here's the best case for pivots. There could be a pivot in every row, so there's a potential that this mapping T is an onto mapping. But note, there is not a pivot in the far right column of this non-augmented matrix. So over here, there's no way it's linearly independent. This is an if and only if, so if it's 1 to 1, there would have been a pivot in every column. And if there is a pivot in every column, it's 1 to 1. So one of the conditions fails, both of them do simultaneously. All we have to now say is, focusing over here, there cannot be a pivot in every row of A. Now we need a conclusion. That's pretty much our explanation with the figure on the left. The conclusion goes like this. This implies, let's use a special color here because it's easy to get mixed up. Our conclusion is not about A. That's just how we got there. The question is about T itself. So when we go to write our conclusions, we have to mention this implies T is not 1 to 1. So be sure you write down a conclusion that's about the actual mapping, not about the matrix itself. That's kind of a small thing, but it's good to say what we mean and mean exactly what we say with this kind of stuff. Well, any questions at all, folks, on part A there?
Would it be, there cannot be a pivot in every column?
Oh my goodness, that should have said column, absolutely. Thanks for spotting that. This would have been a point deduction on a real exam problem. I think that'd be a -1 for sure. It should have said column right here. And just like I said earlier, it's a bad idea to get rows and columns mixed up, so thanks for spotting that on this one. Other questions, comments, or corrections on this one so far? Okay, let me put this like this. And just so the notes are more readable, let me write this in as a column. Just wanted to show where the mistake was. There we go, can just barely fit it in. So pivot, there cannot be a pivot in every column, means there's no way this one is 1 to 1. Other questions so far, folks? Okay, let's turn this around then and suppose it goes from a smaller space, R3, into a larger 4-dimensional space. It's doing it in a linear way, so that's pretty restrictive in a certain sense. We want to know if it's onto. Onto is generally saying you're going to be able to get to every single vector in R4 in some way by finding some preimage here in R3, some domain element X. But if we're trying to spread out 3 dimensions into 4 dimensions, that turns out to be impossible. Unless you take this out. If it's nonlinear, it can be done. You can scale up from a lower dimensional space and cover a higher dimensional space entirely with the right mapping. But this should be impossible if you do it in a linear way. There's no way to break up your vectors and make them somehow map to everything one dimension higher. That's just the intuition behind it. Like before, we actually have to show it, but it's all about getting the standard matrix. Any questions about the statement here before we start? Okay, let's kind of show how this would go if we were a little bit more terse. We might start by saying, here's the transformation. It's linear, so T of x equals AX, where A is, we find the size by reversing and calling it 4/3. So now we know what we're dealing with for the matrix. Let's just write out a really quick sketch of it. This one has 4 rows, 3 columns, there we go. I always feel like I have to complete that array there, or else it just doesn't seem right. So there's all the potential entries. We don't know the values of any of these entries. We're just wondering, again, what's the best case for pivots? There could be one here, here, and here, once it's in an echelon form. That means, well, this mapping could be one-to-one, as the potential, if there really is a pivot in every column. But there's no way it's going to be onto, because we're missing a pivot in every row. We can't say the columns of A span R4. That's really the whole deficiency here. But now our conclusion goes like this. Let's pay very special attention to row. I'll try to get that in on this one on the first try. Observe that there's no way you could have pivots in every row. So we'll say, since A, let's say this is a stronger way. I was going to say doesn't have, but let's say cannot have. No matter what you do, this is a fact about this matrix. Since A cannot have a pivot in every row, A is, oh, and that's a mistake right there. We shouldn't talk about the matrix A, but it's so tempting. We're just looking at it. We should be saying T is not an onto mapping. Get that out of there and bring back T once again. So the actual transformation, the function itself, not the matrix, is not onto. So these are 2 cases where we can definitely say one way or another that it's not something. It cannot be onto in this situation if you're mapping to a higher dimensional space. And if you're going from a higher dimensional space to a smaller one, that could definitely be onto, but there is just no way it's one-to-one anymore. Many vectors are going to the same actual output in that configuration there. So again, that's what one-to-one onto looks like for these transformations. Any questions at all with part A or B? Yeah.
So it would, excuse me, be acceptable then to reason that there can't be pivot every column of row of A and then go to the conclusion. We don't have to say the columns of A span R then, or
Exactly, yeah. You're able to just go right to these conclusions. If you lack the pivots, then you can just say it's not one-to-one, absolutely. Other questions about that so far? Okay, that's kind of the cool thing about linear algebra now that you mentioned it is a lot of times when you introduce a new interesting technical definition like onto, one-to-one, there's a lot of connective material that connects all of our definitions. But what we really want to do is essentially go from, say, the statement of one-to-one all the way down to this. And that's pretty much our goal in linear algebra. Try to cut through all this stuff as much as possible. And here's one wild way we're about to do that. Just to take a really quick preview. We're about to look into matrix operations, inverses of matrices. Let me show you the document that we definitely will have on our second exam. It's going to be somewhere on a last semester. So in a really great sense, this is pretty much what linear algebra is all about when it comes to organizing theorems and definitions. If we have a square matrix, then we're going to relate all of these ideas together in the sense that they are all simultaneously true or they're all simultaneously false. This is like our theorem 4 that we saw from chapter 1 that was printed on exam 1. It just has a lot of interesting and extra things here. We have information about onto, one-to-one, that all get relayed together if your matrix is squared. What's so special about a square matrix? Well, if we go back to our current notes, if there's a pivot in every row, there's automatically a pivot in every column and vice versa. So for certain state transformations, you're going from R4 to R4, one-to-one and onto, they're completely the same now. It's all about, do you have a pivot in every row or column? They're interchangeable completely. But that's kind of what we're going to get towards. So we cut through a lot of stuff. And this is going to be like our big cheat sheet to not to reason through every single step, but we can connect, say, pivots all the way down to something being invertible or something spanning and so on. So linear algebra, at least the way we're doing it in this course as an introductory course, it's all about those pivots. So finding them, row reduction is the major thing we have to get through to be able to absorb this information. Well, let's take a look at maybe one last one, part D. Part D is a little bit different from the others. It says T of x equals AX, where A is the standard matrix, and it's row equivalent to this matrix right here. So we don't know what the standard matrix originally looked like, but row reduction happened and it ended right here in its reduced echelon form. There's a couple questions. What is the domain and codomain? And word of warning, this is a typical exam 2 question that is usually pretty tricky, I'd say. Let's highlight that right here. We say domain and codomain a lot, but suddenly being on the spot and being asked what is the codomain and the domain, that can be really tricky out of nowhere. So let's put here just as a reminder, this is a potential exam 2 question. I mean, they all are, but I want to highlight this one because if it does show up on exam 2, this one is not the funnest one. But here's how I'd probably identify or work through it. First thing you want to do is just say, what is the size of that standard matrix? This one is a size 2 by 3. It's got 2 rows, 3 columns. And this means T is mapping in this way. I haven't filled in the superscripts. Anyone volunteers for what the size for the domain should be? Exactly. We're just going to take, or hang on, I got a little bit mixed up. It wouldn't be the 2, we have to switch these 2 right here. It'd have to go from R3 to R2. That means if you answer it like this, you've pretty much done it. But to feel like we really answered the question, let's say right here, once and for all, R3 is the domain. R2 is the codomain. So when we do the matrix mapping or linear mapping, T of x equals AX, we're taking vectors from R3 and sending them into R2 altogether. So we've got domain and codomain down. They're asking next, is T one-to-one, is T onto? Let's color code these. These are usually pretty fast questions at this stage. We can say really quick, T is not one-to-one because, and we have to say something, some justification. Any volunteers for what we should say on this statement here? Exactly. We're missing one in column 2. And even if we had it non-reduced, I mean, it's 2 by 3. Like what you said there just cannot be one. So no matter what we do with those entries, by the nature of the size of this matrix, T is not one-to-one because there cannot be a pivot in every column. And by the way, if part D was a real exam 2 question, it'd probably be broken up into maybe 2 questions altogether. I always do 20 questions exams for this kind of work. And so this is a lot of stuff for just one problem, I'd say. Next, for the next part, observe we have a pivot here, a pivot here. That means there's automatically a pivot in every row. And you could say now T is on two. I want to expand on this a little bit. Sometimes people say this in a weird way. You can just simply say T is on two, T is not on two, and that's completely fine. But sometimes the author puts a little bit more words into this. He might say T maps R3 onto R2 since there is a pivot in every row. That's kind of more flowery language if you say T maps R3 onto R2, but it's also visual, so I think that's why the author says it sometimes. But if you see it written out this way, we're just saying, yes, T is on two, just a different way of saying it. What we did, folks, that's our rundown with transformations. Again, if you get curious on why we're focusing so much on them, they're everywhere in mathematics, and the more math you take, the more abstract algebra you take, the more you're going to be getting into this kind of situation, dealing with isomorphisms and seeing which types of mathematical objects are truly the same as others. Linear transformations are just the right kind of terminology to make that happen. But another thing we can do, and this is kind of the choose your own adventure portion of the class, I wrote an application if time permits, but we kind of are not right on the right schedule at the moment. We are just about to go from 1.9 into section 2.1. So I'll leave this completely up to you folks. Would you like to cover this application here, or would you like to go to the next section? Any volunteers for one direction to go? Oh, we've got one over Zoom. Quentin says, let's cover it. Awesome, let's give this one a try. It's kind of fun because if you're in this class, you've definitely seen calculus, worked with integration, differentiation. Prem also agrees. Awesome, thanks folks. And so this is a great way to say linear transformations are not exclusive to linear algebra. We kind of hinted at that at the bottom of the notes, but it's really everywhere. You've been dealing with transformations quite a lot. So before we get too far on this one, let's go back, way back down memory lane. When we were in one of these kind of courses, I want to go to, of all places, let's go to college algebra. So I thought I had it listed here. I should try to get these tabs ready to go before I try to jump into something. Okay, we're almost there. So this stuff, this is from quite a while ago. Now, if you were like me when you first studied college algebra, dealing with function composition, function operations, this stuff might have just seemed weird because the sum of the functions is just add two things together. Nothing seems special there, and it didn't seem to be emphasized too much other than the cool things you see on the graph. But this is actually the vector addition of two functions when functions come from a vector space. There was one thing missing here, but there's all sorts of other function operations. But this is now vector addition, as weird as that sounds. So we can take this information, go back to the notes. That's exactly what this is right here. By the way, this is what makes chapter 4.1 kind of abstract in a certain sense. Vector spaces don't have to be R2, R4, and so on. They could be things like this. The set C01. Bracket 01 is a interval notation, so the bracket is including 0 and including 1. It's the space of all continuous functions with that domain, the closed interval from 0 to 1. Those functions are nice because they are always integrable. They always have a maximum and a minimum that you can find, an absolute max, an absolute minimum. This turns into a vector space as long as you define the operations just right. So this right here is vector addition. Really, it's just call back to college algebra. We define the addition of two functions as vectors from this vector space as add the two functions with t, just take f of t plus g of t. Scalar multiplication goes this way. If you scale the function, it's written this way. This portion is just the name of the function, c times f. It's wrapped around with t just to give it the function notation. The only reason there's parentheses around the whole thing, the CF, is just to say CF is one object. That's the whole function itself. But you could say scaling the function just means take f of t normally, and multiply in this ordinary way. We're just multiplying by 5. Doesn't seem like much, but these two things give us a vector space. And now that this is an honest vector space, this turns into a transformation. The question now is it linear? If it is a linear transformation, every piece of work that you do about linear transformations applies to this case. For example, information about one-to-one, onto, you can all turn that around. It gets super abstract, but it would apply to the space of continuous functions. And here's what our operation T is going to do. It takes f, outputs an indefinite integral of f, so we're just finding an antiderivative of this thing. An antiderivative will always exist by the fundamental theorem of calculus part 1, so this is well defined actually. So to get at its linear, let's steal some stuff here just for extra help. We'll view it through that lens and determine for ourselves if we really have a linear transformation. Okay, I think we can park that there. And here's how we would start. We have to track through this definition pretty carefully because for this kind of transformation, there is no standard matrix for us. We need to work completely abstractly through that definition. But it's not so bad. It says, here's how you start. You have to pick arbitrary u vectors, u and v, in the domain of T. The domain is right here, and vectors this time are functions. So we'll use f and g just to emphasize the new nature of these things. We'll start by saying, let f, g be in C 0, 1. All we know about those two functions then is that they're continuous on a closed set from 0 to 1. That means their integral really does exist. Both of those are defined for both functions. But this is the next thing we have to take a look at. We wonder what is going to happen if you map this way versus this way. So we need to verify equality here really holds. So once you grab your functions, the next operation to do is literally that. So let's do it right under here. T of f plus g. Once we have those two functions, we go to the transformation and see just what it does. It comes up here and it integrates the sum of those functions. So here it is. Integrate f plus g. At this stage, we'd give it the variable t dt. So that's what the transformation does. At this stage, we're kind of stuck, but that's what this is for. The sum of two functions is broken up in this way, so we're just going to use that directly right away. This becomes the indefinite integral of f of t plus g of t dt. This time the outer parentheses is a stylistic choice to say both of these functions are being integrated. Some people would drop them and just write it this way, but that's completely up to how you just present your integrals with a sum. Some people like to put a parenthesis here to just capture everything inside. But at this stage, we can now borrow on our knowledge about calculus. We know from calculus that the integral of the sum of the functions is the sum of the integral of those functions every single time, as long as they're integrable. So this then turns into integrate f of t with respect to t plus integrate g of t with respect to t. Now, the moment we look at these, we're pretty much just reverse engineering from here to here. This one is just an interesting way to say t of f, because that's what the transformation does. It integrates the function. So from right here, that thing is just one way to say transformation of f, find its indefinite integral. This one does the same thing. It's the transformation of g, find its indefinite integral. And that means we got to this stage. We were able to take that sum and break it up into a different sum. That's half linearity, so we're just about there. If we can show this holds, then every single speck of information about linearity, not just in this course, but all available knowledge, now applies to that process, because we'll have proven it is a linear process in fact. So that's the way linear algebra is typically just everywhere in mathematics. It's kind of surprising. For example, if you go to solve differential equations, your solution set is just a spanning set. You're spanning the right functions to generate all solutions for your differential equation. Well, let's see if we can get property 2 to work out. And then if it does, we'll say it's a linear mapping. Any questions at the moment so far, folks? Okay, let me see if I can zoom out just a touch on this thing. So we define 2 arbitrary functions. For me, when I write out these kinds of arguments, I usually think of these 2 now being in the scope of the entire argument we're writing. So right here, where it indicates a new vector u, I'm just going to reuse f. The only thing we need is now an arbitrary scalar c. This has to work for every single scalar, whether it's 0, 1, square root of 52, something like that. That means we have to work fully arbitrary and start by saying, let c be in R. So now it's just an arbitrary scalar. We're not going to specify what it is. Next thing we're going to try to do is look at this portion of the equation right here. T of c times what is f now for us. That's right. Then the transformation T of c times f, what we'll do is drop it right up here. C times f is going to go into that location. So it's going to be the integral of c times f. Again, c and f are now thought of as one whole symbol. That's just the name of a brand new function. We put parentheses around it to emphasize that. The next set of parentheses are just function notation. And we like to put our dt there just to remind ourselves we're integrating with respect to t. Now this thing is kind of frozen in place, but our definition for scalar multiplication in this new vector space is c times f. It becomes c times f of t. So really nothing major seems to happen here. It becomes, from that formula, the integral of c times f of t, where the multiplication here is just for emphasis. This is ordinary real number multiplication, whereas that multiplication was scalar multiplication in a vector space at a whole different definition. But now we're here, we can fall back on our training from calculus. A scalar right here can be factored right outside the integral. In fact, we often do that just to organize the integral and not worry about constants inside of it. So here's the constant c. We leave behind the integral of f of t, dt. But now that we're here, integral of f of t is just the transformation of f. So this turns into c times the transformation of f. If you carry through all these equalities without ever breaking it, it shows that we got to that second portion. C was factored outside of the transformation. There's no reason to expect that works for every transformation, but it should if it's linear. So we just found out that this transformation of just simply find an antiderivative of those classificational functions, it is linear. Oh, let me try to get the yellow off, and we'll put it in our conclusion. These were meant to be temporary emphasis, but they're sometimes hard to take off. So we can now say this shows T is linear. Deserves an exclamation mark. Lots of stuff from calculus is linear. If you look over your formulas from calculus, this works with limits, this works with derivatives, this works with integrals. This whole process always seems to work. So it's not just integration. Indefinite integrals or definite integrals are linear. So is the process of taking a derivative. Sometimes we call those differential operators. If you ever call it an operator or hear it called a differential operator, that person is probably thinking from a linear algebra standpoint because their transformation here is synonymous with operator. You're going from one space back into the same space. Well, that's our extra work on linearity. Because it says here it's a application of time permits, think of this as more, we were just practicing with this a little bit more. This one would not be a fair exam question. It was just a little bit extra. Well, any questions at all, folks, on the rundown of this application? Okay, this is a good one to look at early, so I'm glad folks over Zoom indicated we ought to do it. This is the kind of vector spaces we're going to be looking at and working with. When we're over here in section 4, oh, this is not even the right class, is it? Sorry, let me get back to our right Moodle course. Okay, and that thought was this kind of stuff, these kinds of vector spaces, these kinds of functions now being thought of as vectors, is the sort of thing that we're getting into in section 4.1. We still have spaces like R2, R4, but we're now looking at any kind of vector space that seems interesting in that section. So that's why I mentioned this one's probably a good one to pre-read before the class, just to help out make the class make a little bit more sense, I'd say. Well, at this stage, we're done with section 1.9. So congratulations, folks. That's chapter 1. Feels like the longest chapter ever. The other chapters are a little bit shorter. In chapter 2, that one has a lot of sections, but we're only going from section 2.1, 2.2, and 2.3 for our course. So starting off in section 2.1, it has an exciting title. We're dealing with matrix operations. So much like dealing with vectors, we're just seeing what all we can do with a matrix. A couple operations we already know is we know how to take a matrix times a vector. We're going to expand on that. We want to do sums, differences of matrices, rescale them, and matrix multiplication itself. First thing we have to get through, though, is all the notation. So if we have an M by N matrix, that's indicating we have M rows, but it could also be thought of it this way. You write out all the entries in the matrix. A11 means it's in row 1, column 1. A21 means it's in row 2, column 1. And it definitely has M rows. That's AM1 in row M, column 1. So if you see it indicated as an M by N, you should see an M here and an N there in your array of values. So we'll denote Aij as the entry in the ith column, ith row and jth column. If we want to write out a matrix generically, we could either indicate it this way. Here we're saying the arbitrary elements are indicated by A, or we can expand it out this way. That'd be less rare. That's just more indicating how the notation works. So every one of these right here, if we wanted to, let me try to highlight this better. So next, every one of these columns, if we would like to, we could just represent as a single column vector. That's what's going down here in the notation. So if you see A indicated this way, that's because we want to discuss or display the columns more than the original entries. So, for example, A2 is just referring to all of these elements right here. Their second superscript or subscript has 2. A12 just means it's in the first row, but second column. So likewise, if we write out just say a generic one, A equals 534, 0, -83, then our notation allows us to say A13 equals, well, if it's A13, let me take another look at that. That's not even defined. Let me see if I can fix this. Let's call this A12. We could do an A31. That might have been the thought I had, but I definitely switched those out to make it undefined. But just for the sake of practicing our notation, anyone see what A12 should be as an entry from this matrix here? Oh, yes, it's going to be in row 1, column 2. It has to be that 0. Good call. And just for fun, anyone else see where A31 should be? Which entry that one would be? Yep, it would be this one right here. So that's how the notation works. The reason we like this notation is sometimes it's good for indicating how certain formulas might work, like the transpose of a matrix we'll see later on and so on. So this notation becomes pretty common. And I would say this notation also is very common. We've used it before where we just indicate a matrix by listing out what the columns would look like. For example, if we were solving a homogeneous system, AX equals 0 in chapter 1, we would go to here, A augmented with a zero vector, not too much difference from what's being said here. All the columns are indicated there, and that's just the rightmost column. So that kind of notation has been used by us quite a bit as we've gone through. Well, other things that we could indicate are diagonal entries of a matrix. So if we have an M by N matrix, the diagonal entries are going to be these things. You'll know you're dealing with a diagonal entry if you're in the same row in the same column. For the matrix A above, that one will be the main diagonal. And the diagonal entries would be A11 equals 5, A22 equals -8, are the entries on the main diagonal. So our notation's kind of interesting. Diagonal matrices turns out to be extremely important in linear algebra. In fact, part of all of our work is to discuss eigenvalues, eigenvectors. That's really just using parametric vector form in an interesting way, so that we can take a square matrix and do a so-called diagonalization of it. So when we get in chapter 5, that's going to be one of our primary techniques. Try to find a way to diagonalize a matrix. Well, if the matrix is diagonal, it might look like, say, this. A diagonal matrix would have an entry on its main diagonal, maybe an 8, and zeros elsewhere. So the main diagonal on this one would go through that stretch, and we would call this a diagonal matrix. Again, we've seen diagonal matrices tons of times. Another diagonal matrix would be I2. The identity matrix with two columns goes 1, 0, 0, 1. Its main diagonal just has the requirement that those have to be exactly 1. And that's just a different version of a diagonal matrix, the kinds that we see all the time. Other things in our notation to be worried about, or not worried about, but pay attention to is, if we ever have to indicate a zero matrix, we typically just write 0, much like we would have done with a zero vector. The size of that 0 has to be clear from context, and if it isn't, we would be required to indicate it. So say, for example, if we have a zero matrix indicated this way, but I need to show you what the size is, it'd be indicated this way. Maybe it's a zero matrix of size 2 by 3, and then if necessary, we could expand it. It would look like this: 0, 0, 0, 0, 0, 0. So this whole thing can now identify a zero matrix, and if we know the size, if it's clear from the context, we might just indicate it this way. This time I wouldn't put a vector symbol over it, since we usually think of that as a column vector whenever we use that notation. Well, we did it, folks. That's the major notation to be familiar with when dealing with these kinds of things in matrix operations. Any questions at all with these new notations? Okay, with all that said, one thing we definitely need to define is, when is a vector equal? We did that in section 1.3 by saying corresponding entries had to be equal. And now we'll say two matrices are equal if they have the same size and if their corresponding columns are all equal. That just means all of the entries are equal to each other. So this is kind of interesting. This is the reason why whenever we're doing row reduction, we always made sure to write out this. Never that, because if you're doing row reduction, you are changing the entries of the matrix. You are not creating an equal matrix at all. They're all different. And on this example here, it is kind of a silly example. They ask, which matrices are equal amongst the set? Taking a look at A and D, they have the possibility. They're both of size 2 by 2. We have to check their entries. Column-wise are 1, 3, 2, -4. So we can say A is equal to D. But if we look at B and C, well, that just depends on your point of view. I would almost say they're equal. They have the same entries, right? 4, 6, 8, 4, 6, 8. They have the same entries in the corresponding order. The first entry, second entry, and third entry are 4, 6, 8. Same over here, 4, 6, 8. But in matrix algebra, the size of your objects really does matter. It determines if multiplying one thing or another is even defined. It determines what the size of the objects are when you multiply. And so I would say in this whole definition, this is the most important part. That means when you look at this column vector B, it's of size 3 by 1. This one we'll call a row vector. Let's say that right here. It feels equivalent in a certain sense, but algebraically, when we define our matrix operations, it is not equivalent. This one is of size 1 by 3. And so we'll say here, B is not equal to C. So which matrices are equal? Just A and D on the far outer ends. Any questions about that so far, folks? Okay, so we have a notion about matrix equality. Let's see what we're getting into next on this. This is the portion of the notes where I've made a weird note. This should absolutely feel like deja vu now. We did this exact same work, almost, when we were in section 1.3. The only difference was we had column vectors and nothing else. So we are redefining all of this work for matrices A and B of the same size, m by n. That means we're working in a new space, R m by n, for m rows and n columns. And this is just going to turn into a brand new vector space. We just have to give the right definition for vector addition and scalar multiplication. But if you look at these, it should feel almost the same. In fact, let's take a look back in section 1.3. I think I have that pulled up. It's literally the same kind of stuff. We were back in the land of vectors this time. Vector addition just meant add up corresponding entries. Scalar multiplication just meant scale up all the entries by that common scalar C. Over here in 2.1, same exact thing. The entire matrix A is represented as Aij. I mean, that's a huge notational advantage because we're not putting this in, but that's what we mean, that entire matrix, when we say Aij. Next, the entire matrix B is represented by Bij, so same notational idea. Vector addition looks like this. Just add up the corresponding entries from the matrix A and the matrix B, but do it for every single entry now. There could be quite a lot of them. Scalar multiplication just says, take your entry Aij and just rescale every single one of them. Here's what it looks like. All of your entries are rescaled. So that's now scalar multiplication. So in other words, the Ij entry of A plus B is just add those entries, Aij plus Bij. The ijth entry of C times A is just C times Aij. And that makes Rn by n into an honest to goodness vector space now. So we have interesting vector spaces to take a look at. Just like in the last section, in 1.3, once you have a vector space, there's some properties from vector spaces that you can use and take advantage of. Our properties in this section go this way. First up, we have the commutative law. You can either take A plus B or take B plus A. Same difference, or no difference is a better way to say it. You get the same exact result. The reason it works is up here, that's ordinary real number addition, and you can just change the order. No problem there, and it works out just fine. This is the associativity law. Thank goodness we have associativity in this kind of algebra. If we didn't, that would be extremely weird, and there are algebraic systems that lose associativity. So that says, if you're adding A plus B plus C, you can either add the first two or the last two. And what it means is you can just drop parentheses altogether. There's no ambiguity here. You can add whichever ones you'd like to add up first. This one is the identity for vector addition. If you add a zero matrix to A, you should get A back. And that makes sense because if you're adding a zero matrix, all of these things are zero. There's no change inside here. We have a distributive law where scalars can distribute across. We can also distribute a matrix across two different scalars and get that result. And this is a form of associativity, but just for scalars. Either scale A with S, or multiply R and S together and scale A by both. You're just going to get the same exact result. Again, every one of these is proven by just looking at what should happen with ordinary real numbers. We're carrying over those algebraic properties from the real number system into Rn by n. So kind of weird, but nice properties. These are not properties we typically go back and take a look at and cite every time. It's just a listing of these are those things you can take for granted each and every time you're dealing with these operations. Again, no different from these properties when it was just vectors. So first thing we should do is practice with this stuff. Looks like I made a addition on my notes right here. I don't think this is on the actual notes on the Moodle webpage. I think I threw this in because it just seems like a good one at the end. Sorry for that. I usually give you a heads up if I make a addition to my notes. But what we've got going on here is just 3 random matrices, and we want to do these operations if possible. If it's not possible, we'll give a short explanation as to why. Feels like this ought to go on the next page, actually. Let's just drop it over here. Let's focus first on 2a minus b. First thing you want to do is definitely look before you leap. The only way that operation is defined is if the matrix A and B are of the same size. They're both 2 by 3, so it looks like we can make this work. First thing I'd probably do personally is just rescale A. So I'm going to double all the entries. We'll have 2, -4, 0, 2, -8, 0. So we've doubled all those entries. And now I'm always worried about extra negations and flipping signs a whole bunch. So I usually rescale B by -1 as well. So I'm going to add right here. Scale all this by -1 gives us -4, -1, -3, -7, +9, and 0. At this stage, we're just adding corresponding entries. It's kind of relaxing in a way based on some of the linear algebra we've already seen. So here to here, we're going to get -2. On this entry, it's -4 minus 1, so -5. This is 0 minus 3 for a -3. 2 minus 7 for a -5. Next, -8 plus 9 for a +1. And 0 plus 0. We did it, folks. That's the work on 2a minus b. Again, not too different from when we were doing linear combinations of vectors from before. Now it's just a linear combination of a matrix. Let's try this one next, b plus c. So if we're doing b plus c, imagine this is a real exam question and you're worried about this. If it's not possible, we need to give an explanation. And this is not looking too possible, right? B is of size 2 by 3, C is of size 2 by 2. There's no way to add a -9 to anything. There's missing entries, right? It's got to be undefined. But if this was in a real exam question, this is all you really have to write. B plus C. Let's put in the size of B, it's 2 by 3. The size of C is 2 by 2. Then next, I would probably just say, from circling these two, undefined. And that works for me as an explanation. You don't have to give an in-depth explanation if you don't want to. But if you did want to, you could add these further notes. This is probably better for notes. You could say it's undefined. The matrices are not the same size. So again, that's the problem right here. They have to both be 2 by 2 or both be 2 by 3, or these kind of operations are completely undefined. They belong to different vector spaces, in other words. Any questions at the moment with those two? Okay, well, let's give this last one a try. This one is the one that I just sort of wrote in out of nowhere. Forgot I even did that. I'll try to keep that kind of stuff down to a minimum. Let's go with purple since it kind of matches the red on this one for color coding. We're taking C minus 6I. And you know what? I2 wasn't really necessary there. I2 means it's a 2 by 2 matrix, but we could just assume that if we were taking C and it's of size 2 by 2, it ought to be 2 by 2 here. The reason I would print a 2 if it was an exam question is so that we don't call it undefined. We know its exact size and there's no ambiguity at all if it was a real exam question. So let's bring it down there as well. So C itself goes 4, -1, 12, 6. I'm putting plus because I'm going to rescale this -6 into, I'm not sure where I'm looking at, the identity matrix, which is over here. The identity matrix takes this form. 1, 0, 0, 1. So scaling it by -6 is just placing a -6 on the main diagonal now. But that means you're only affecting the main diagonal of the matrix C. Everything else is copied. So if you're ever adding a diagonal matrix, and this becomes a great shortcut in chapter 5, really you want to just train your eyeballs to looking right here along the main diagonals. That's the only change we're going to see. So first, it's going to be 4 minus 6 for a -2, copy -1, copy 12. Next, it'll be 6 minus 6 for a 0. And we did it, folks. That's the full matrix operation on this right here. Any questions or comments so far on getting through these? Okay, awesome. Well, again, we're kind of just re-going through all of this stuff. And the problem we just did is pretty much just like this right here. So you can expect a couple quick type of problems like this on a second exam, just being familiar with these kinds of matrix operations. And always watch out for something that's undefined. That's a nice quick one to always toss in there. So after doing all these matrix operations, here are the interesting ones coming up next. Matrix multiplication is extra special linear algebra. What makes it special is if you have a transformation T going from, say, Rm into Rn, you can represent it by saying T of x equals A times x. Well, if you're multiplying two matrices together, this is true function composition for those kinds of transformations. So that's a great way to think about A times B. This is a function composition in actuality. But let's take a look at the definition. It says, if A is of size m by n, let's circle this component right here, and the matrix B is of size n by p, with columns B1 through BP, then the product of A times B is a m by p matrix. Note the m right here comes from the number of rows of the first matrix. P right here comes from the number of columns from the second matrix. And the way we generate these are, well, we go back to section, I believe this was 1.5. All of these are our matrices times column vectors. So on one hand, we use our notation from before. This is the matrix B. These are just the columns. So this is still A times B. And A is just going to multiply every single one of those columns. So we're going back to a matrix times a column vector. Let's say for the sake of warm-up, let's just do an arbitrary matrix times a column vector just to get our mind into that right zone. So let's actually call this a warm-up because that's exactly what it is. So here's our matrix. Let's make it square. 1, 2, 3, 4 sounds like a perfectly fine random matrix. Now it has to multiply something of size 2 entries, so 2 by 1. Let's put 5, -3. And when we multiply in this way, you can write it out, say, on the margin, but I encourage you to make it a faster process because you don't want to break down a big expansion for every single one of these columns. Multiplying your matrices could then take pages if you wrote out every single arithmetic operation. So shortcuts become kind of part of life or survival for this kind of thing. When we try to get this entry, all we're doing is we're taking this row, imagine kind of flipping it so it overlaps with 5, -3, or making your 5, -3 come over here, multiply the corresponding entries and add them up. So this will be 1 times 5, so we're up to 5, plus 3 times -3, it's 5 minus a 9 for a -4 right here. So that generates the first entry. We want the second entry. The only thing we change is the row that's being multiplied. So now we'll have 2 by 5 for a 10, plus 4 by -3, -12. So it's 10 minus 12 for a -2. So that's what we did back in, say, I think this was section 1.5. It's getting a little bit foggy at this point. And now we're expanding on it because we want to calculate the entire matrix times another entire matrix. Just means we're doing these kinds of things repeatedly, but we need to show the process of doing this in a more streamlined way as well, so matrix multiplication doesn't take way too long every single time. Well, let's take a look. We have A and B right here. It says compute A times B, B times A. If we have an undefined product, we'll just give a quick explanation. Let's start with this one, A times B. First thing we want to do is, again, always look before you leap. A is of size 3 by 2. So let's put 3 by 2 here. B is of size 3 by 3. And already we have a problem. Up here, matrix multiplication only works if these two inner dimensions are exactly the same. Here, the number of columns is not the same as the number of rows. And so our whole problem is right here. Again, if this was a real exam question, this is pretty much all you have to do. Show me why it's undefined by saying the size and indicating where the problem is. That's not quite right though. Let's target this a little bit better. The problem is right here. Those two inner dimensions have to match up. Sorry, I'm missing when I circle things. That was really weird. But if those match up, everything's fine. We can multiply. If there's a mismatch, the whole thing is undefined. And if you want to write out a longer explanation, you could just say undefined since, let's say because the number of columns in A is not equal to the number of rows in B. Or in other words, that's the problem right there once we circle the right things. The kind of nice thing about that is that's the exact same things we looked at up here when we were doing a matrix times a vector. We always looked at those inner dimensions. So this one was a size 2 by 2. The vectors of size 2 by 1. Those match up, so we expect something that's defined. Well, A times B had no meaning on this problem. Let's turn it around to B times A next. So looking at it from this point of view, B is of size 3 by 3. A is of size 3 by 2. That means this is defined. If it's defined, that means we have some work to do. And a really good idea is, let's just write out the matrix B right here. This becomes highly, highly visual. So column-wise, B is 0, 4, 8, -1, 0, -1, 0, 2, 7. Matrix A is 2, 3, -1, going column-wise again. Or excuse me, 2, -3, 1. And 1, 4, 6. Let me take that highlighting off temporarily, or actually permanently. Next thing you probably want to do is indicate the size of the result. It's the outer dimensions that tell us. The resulting thing will have 3 rows, so I'll make it be at the same height. But we're only going to get 2 columns. Let's make that a little bit skinnier to emphasize that. And now the definition of this goes like this. We're just going to take A times the first column vector. So this whole matrix A times this gives us a result going right inside here. That's essentially what the process is going to look like. But again, color coding is not a bad idea with this. We're going to generate out stuff in here by using only that column vector. The column vector to the right is a pure distraction. It's going to give us information on the rightmost column, but we're going to build out the first column to start. Next thing we need to know is, what are the entries? Color coding might not work as great for here on yellow, but I'll highlight it this way. If we multiply this vector with this vector as the typical products, we get an entry right exactly here. So let's make that happen. It'll be 0 times 2 for a 0, -1 times -3 for a +3, and 0 times 1 for a 0. All we get is a +3 on that product there. Does that make sense to folks so far, getting the 3? Awesome. Next thing we do is we change our focus. If this was all on a chalkboard, what people typically do is they move one finger this way and another finger that way, and they multiply. It's kind of hard to do on Microsoft Word, so I'll just use highlighting correctly to show that. So for this entry here, I guess we can kind of make the color coding work a little bit. We'll get an entry in that location. And because we're in the first column, we're only using the first column on this. So it's going to be 4 by 2 for an 8, plus a 0, plus a 2. That gives us a 10 altogether. Then it's rinse and repeat. We want the entry down below. We're going to use the next row down below to emphasize. Let's change the focus to here. Same idea, it's going to be 8 by 2 for a 16. Negative 1 by 3, so plus 3, we're up to 19. Plus 7 times 1, so 19 plus 7, looks like we're up to a 26 on this one. Let me know if my numbers go sideways. That's pretty easy to do now that we're doing matrix times a matrix. But there we've done it, folks. That's a matrix times one vector. We're going to change it up. Use these entries right here, and that's going to generate our next column vector. If we want this entry, we just use this first row again, and it's the same exact process. Just rinse and repeat. Again, above, that's what the definition is trying to convey. Take A times B1, that's what we got right here. A times B2, that's about what we're doing right here, and this is the B2 column. So let's work it out. It's going to be 0, negative 4 plus 0, so negative 4 altogether. Next, change the focus to the next row. And we'll get an entry right here. I think I accidentally took off too much. I want blue here as well to show where things are going. So it's going to be 4 by 4 plus 0 plus 12. So that's 4 plus 12 for a 16. Then finally, for this last entry, we'll change our focus to the last row in the matrix right here. But same exact task. Take 8 times 1 for an 8. Minus 4, we're down to a 4. Plus 42, that's going to be a 46 altogether. Numbers look bad, but they didn't turn out terribly bad. And finally, we've done it, folks. This is the result for the product. To keep a little bit of color coding, you might think of this as the blue column, this one as the, said that weird, green column, and this one has the blue column. Just to indicate how we got these entries, we were using that column, this matrix times that column to generate that one, and vice versa. Well, how do folks feel about that? Does that process make sense for matrix times matrix? Awesome. It's one of those things that does take some good practice, so there's plenty of these kinds of things in the homework. The homework is very just crank out multiplications and that kind of stuff. But once you get good practice on it, really there's not a whole lot of writing. It's just a lot of tally as you go. For real exam questions, I do control the numbers. Once it's getting like this on row 3, that starts to look like an annoying question to me. I probably would change like some of these to like a 2 or maybe a 1 right here. Maybe an extra 0 here and there. But finally, that's a matrix times a matrix. And if we're taking a matrix times a matrix, these can sometimes be thought of as a matrix in its own right. We would typically call that a row vector, like we saw at the top of the notes. And this one is a column vector. But so far, our algebra for a matrix times a matrix will allow us to multiply both of these together. It's kind of surprising. So this first one, part A, says, compute A times B. This is a really important operation and something we're going to delve into quite a lot. In Calculus 3, you look at it as well when you're in higher dimensional spaces. And the reason for that is, if you take a row vector times a column vector, it's either going to be called an inner product or a dot product, and it's used to construct the geometry of your vector space. This simple operation is going to allow us to measure angles between vectors, measure distances between vectors, which means you can now do calculus on a vector space once you have distances and angles between those vectors. Also keep in mind, vectors don't have to be like these. It could be an entire function. So now with our theory, you could ask weird questions like, what is the angle between two arbitrary functions in a vector space? So the inner product is really important for us. And here's a preview of how it goes. Here's A times B. Again, you always want to look before you leap, even if you're assured things are defined. This one's going to be size 1 by 3. 1 row, 3 columns. B is of size 3 by 1, 3 rows and 1 column. And note, it is defined. The inner dimensions match, and the outer dimensions are both 1. That means this is sometimes called scalar product, which is not a bad name when people call it a scalar product because the result is a literal scalar. This is the one time where we're not even going to put a bracket around it. If we're getting a 1x1 matrix, a bracket around it just seems silly at that point. We'll drop the bracket. But before we get there, let's write out A, it's 3, 2, 1. Write out B, it's 2, 3, 0. And when you think back at when we did this product, B times A, we were just doing this over and over again. In fact, we did it 6 times to generate all of those entries. Every one of those entries is an honest dot product. So here, we're going to get 3 times 2 for a 6, plus 2 times 3 for another 6, plus 1 times 0 for a 0, and we get 12 as the result of that one. Mysterious operation. Again, it's kind of impressive. This allows you to define distances and other interesting things for an honest geometry on your vector space, whatever the vector space could have been. Now, this one is weird. I'm not as familiar with this at all, but I did some research, Wikipedia, and this one's called the outer product. It's not in bold because it's not something we're going to cover in our course. But if you're curious about the applications, there's things like image compression, signal processing, and quantum field theory. We might have to ask Barnaby, our resident physicist, about that one. But this product turns out to be really rich in applications out of nowhere. This one's also defined, so let's take a look. B times A. Well, B is of size 3 by 1. A is of size 1 by 3. So yes, it works. Inner dimensions match. Outer dimensions are 3 by 3. So we're going to get a full-on 3 by 3 matrix from B times A. To properly see how it goes in, let's write out B. It's 2, 3, 0. Write out A. It goes 3, 2, 1. And we have a 3 by 3 resulting product. To help us through this, let's carry this down as a temporary screenshot because we're pretty much just going to copy that pattern. Probably doesn't have to be that big though. Let's fix that. Well, any questions first, folks, before we go for this outer product here? Okay, well, let's do this kind of idea with the color coding. I want to generate the first column among 3. So if we're in this column, all we care about is that entry. And what do? Well, if we're wanting to get this entry, we're going to take the first entry here, multiply by the 3, giving us a 6. We want the second entry, we just move down 1, take 3 by 3 to give us a 9. Move down 1, it's 0 by 3 to give us a 0 right here. So we've expanded out our first column vector. Next, let's do this one. Will give us results going inside here. And we're just reusing 2, 3, 0 every single time. It's actually kind of fast to visualize because it's now just 2 by 2, 3 by 2 for a 6, 0 times 2 for a 0, then rinse and repeat. Does that make sense to folks so far with that process? Awesome. Let's do one last one. I'm running out of color, so I'll just use yellow this time. So for that entry, I mean, it's even nicer. If it's a 1, you're just taking 2, 3, 0 and dropping it right in. So in other words, the values here are just telling you what you're scaling the column vector by, giving you these results. So it's going to be 2 by 1 for a 2, 3 by 1 for a 3, and 0 by 1 for a 0. And I just noticed by looking at the clock, thanks to folks who have put away their notebooks, I went way over on this one. Sorry about that. Must have been just kind of an exciting problem, but I'll make it up to you on the next problem. So maybe we'll end a few minutes later. Any last questions before we call it a night? Okay, well, have a great night, everyone. And sorry for running over it. I guess, again, this one looked kind of fun for some reason.
Thank you. Have a good night.
Thanks, you too.